Okay, so now we are going into mechanics of machine, sort of like introductory only lah, okay? I think as you all go through your uni course, right, you all would have a module itself on mechanics of machines. Okay, so machines consist of multiple parts, as you already know. So their members link together to perform some useful function. Right, we create the machine so that it can help us do some stuff. In mechanics of machines, this topic, we are concerned about how motion can be converted and transmitted from one member to another. Okay, that means one part moving, then this part connected to many other parts. Then we are interested to know how at the end, right, the outputs, how it works, what is the velocity, what is the power transmitted, etc. So there are a few ways to transmit motion. First way is via direct contact between two members, such as between a cam and follower or between two gears. So this is direct contact. Gears, right? Gears look like that. Okay, they appear in our gearbox, vehicle gearbox. Bicycle also have, in watches, all this. Okay, so gears, when something turn right, if you put other gears around it, the teeth will eat into the other teeth and then will start rotating the other part. Okay, so this is direct contact. And then cam and follower, right? When we say cam, it's something like this. It will have this rotating component. Okay, it will go in rotation. Then it will be designed in a weird shape, such that at some end, right, there will be this thing called the follower. It will move according to how this weird shape wants it to move. Okay, so this is actually a simple cam and follower design. Okay, if you have this protruding shape, you see when the protruding shape comes to the top, right, this thing will pop up and down, then stop there, then continue later when the cam reaches there again. Okay, so this is a cam and follower system. So this is also direct contact, as you can see. They are touching each other. Okay, and then motion can also be transmitted through an intermediate link, or we also call it the connecting rod, such as linkage mechanisms. This you can find it in internal combustion engine if you are familiar with the piston. Okay, basically it will look something like that. Engine rotates, right? So there will be this rotating component. This one on the left that's rotating 360 degrees, and it will rotate over and over again. At the other side, you have this thing that is sliding only left or right. Okay, it's a slider, only will go in one direction, back and forth like this. Okay, so from the circular motion, right, we want it to change to back and forth, single direction motion. How do we do it? We have this rod, right, in between. Can you see this rod that's rotating 360 degrees? It's connected to this slider, right? This rectangular slider via another rod. There is a rod in between them. That one is the connecting rod. Okay, so this is via an intermediate link. We send the motion, we change the motion, and then we pass the power on. Okay, then the third way is by flexible connector, such as a belt or a chain. This one you all will be the most familiar. It appears in bicycles. Okay, basically when you have chains, this chain can be very long also. Basically, you turn here, right? Then via this chain, you can turn something else somewhere. Okay, depends on where the chain is connected to. So we come into cam design first. Any cam design must comply with these constraints. Cam function must be continuous through the first and second derivatives of displacement across the entire interval. So this is the requirement, okay, for a cam design. This is the cam, again, this is the cam, and then this is the follower. Okay. Basically, this thing is called a follower because this thing follows the motion of the cam. Okay. Then the first point, what does it mean? First and second derivatives of displacement, right? That is actually your velocity and acceleration. So it must be continuous throughout the entire motion. You see 360 degrees, right? there must be some sort of function to describe all this displacement, velocity, and acceleration for this thing to make sense. Okay, so that's one of the criteria. Second one, the jerk function must be finite across the entire interval. Jerk is third derivative. We are not so familiar with this, but you can see as you see first derivative is velocity, right? Second derivative is acceleration. Then actually you can move into another order. It's the third order. Okay, that thing is called the jerk. So velocity, acceleration, and jerk. Basically, jerk is the rate of change of acceleration. Okay, so that must be finite across the entire interval also. For complex mechanisms, KEM motion cannot be defined using single mathematical expression. So there may be a few piecewise function combined together. You see this one, 360 degrees, right? If it's simple enough, you can write one mathematical equation to describe this entire motion. But imagine across these 360 degrees is super complex. Maybe 0 to 50 degree, there's a certain weird motion. Then 50 to 200 degree, the motion change already, become another weird motion. Then 200 to 360 is another kind of motion. So you can break them down into three, for the one that I just described, into three piecewise function to form this, to describe this complex motion. Okay, so it can be broken down also. Motion of KEM can have many variations, and these are just three more common ones lah. So we have rise fall. That means the follower rise and fall. Then you will continue to rise and fall, rise and fall. Okay. Second one is rise fall dwell. Dwell is okay, it's actually here. Dwells are defined as no output motion for a specific period of input motion. So you see, right, it moves up and down, and then at this period of time, right, it stops there. The stopping part, right, we call them dwell. Okay, so this system here that you see, right, is rise, fall, then dwell. Okay, then you'll continue rise, fall, dwell, rise, fall, dwell. So this is the motion of this KEM that is designed. You also can have rise, dwell, fall, dwell. That means you rise, then stop, then fall back down, then stop again, then rise, then stop, and so on. Okay, so you can design it to have any kind of output motion you want. The equations for simple harmonic motion for rise motion. So rise is when this follower go up, the rising motion. The simple harmonic motion can be described using these expressions here. So S is the displacement, V is the velocity, this is acceleration, this is jerk. Basically, this is first order, second order, third order lah. Okay. And then this H is the total rise in meter. That means what is the amount that this thing can rise in total. Okay, that's H. Theta is the camshaft angle in radians or degrees. Depends on your calculator mode lah, okay? So there's a cosine or sine in front, right? So it can be in any mode, but then make sure you put at the correct mode. Okay, if you ever need to use that. So that is the angle, camshaft angle. It depends on how much this has rotated. Okay, so the angle could be it has rotated 50 degrees, it has rotated 180 degrees, which is to point the other side. Okay, and so on. Then beta is the total angle of any segment in degrees or radians. Now we are talking about rise, right? That means you see this, the part where it rises only, like how many degrees is describing that, is for that. Okay. For example, you see down here, it's only when it's here to here, around here to here, where there's a rise motion only. Okay, so the angle will be from somewhere here to somewhere here. Okay, maybe 30 degree, maybe 40 degree. Of course, I wouldn't know from this image. Okay, that's what beta is trying to say. So here's to show you some common KEM and follower arrangements used in engineering applications. First one is KEM with inline knife edge follower. So you can imagine when this thing turns, right? This thing will go up or down. Okay, basically like the one we see just now. Cam with an inline roller follower. Also, it will result in similar motion, but the contact is different. Okay, the contact is different, may result in slightly different motion, and also the wear and tear will be different also. Okay, you can imagine different designs will have different usage and then different maintenance for it also. Okay, cam with an offset roller follower. So instead of staying in the middle, right, that means in the same as where the shaft is, the rotating shaft is, if you offset this motion, this follower motion, right, will be slightly different. Okay, the rise and fall may be at different angles and then for different duration also. You also have cam with an oscillating roller follower. So you see as this thing rotates, right, maybe this thing will go up and down like a wave. Okay, maybe here go up first, after that here will go up, then here will come down, and here will come down. Okay, so we have really many different kinds of cam and follower designs. This cam application is found in our internal combustion engine. Okay, you know when in a typical engine, right, you need to take in fuel and air. Okay, you need to take in fuel and air into this cylinder before you compress and then you spark it. Or in diesel engine, it will ignite on its own lah. But the the engineering to let the system know when to take in the air and the fuel, right? Something must open and close, correct? At a certain timing for the air and the fuel to go in. Okay, is that part, right, is settled usually by cam. Okay, camshaft. So it will look something like this. The cam and the shaft, the cam and the follower will look something like this. These are two different designs. Okay, so this is the simpler design. Imagine you have the camshaft rotating. This thing, right, will follow this camshaft, then it will open and close. All right, open and close. So imagine you have the cylinder below. Imagine you have the cylinder below. Imagine this is a cylinder, okay? So down here, combustion happen. Okay, combustion happen inside here. So air and fuel can come in from here, right? So this thing open and close, such that you can time when the air and fuel will go in. Okay, so it's a very common application in engines. All engines will have it these days. Okay, if you go and see car specs, right? Sometimes they will also write it in their specs. Okay, how many camshafts are, what kind of technology they use. Okay, so those are cams. Now we come to gear trains, which are basically gears. Gears are used in all kinds of machines, from clocks to cement mixers to sophisticated aircraft carriers. So gears are one of the most common things for us to transmit motion. Okay, used to transmit rotational motion and power. Imagine you turn something, right? Then some other gear that's attached to the first gear will turn. Okay, so you have some energy transmitted. So is power also. Then this could be also connected to another gear, which will then power something. Okay, so in this way, power is transmitted. Useful for changing speed and torque of a rotating device. Because you see the gears, right? They are circular. They imagine the first gear, you have a certain angular velocity. All right, it's rotating at a certain speed. But you have a smaller or bigger gear. In this case, it's a smaller gear that is attached to the first one. Okay. In this manner, the second gear will have to rotate at a certain speed to match the teeth of the first one. Okay. So if it's a bigger one and a smaller one, the speed of the smaller one will be increased by a lot. Okay, because one teeth must go inside, must match the other one, correct? But this one has lesser number of teeth. Good mechanism to transmit torque at high efficiency. because they are locked well and do not slip. So you can imagine these are metals, usually metals, touching metal of the other part. If they are rough enough, they will just, at the point of contact, when it's pushing the other one, for gears, it will hardly slip. Okay, so when things don't slip, right, it doesn't lose so much energy. I wouldn't say it doesn't lose energy, but it loses less energy compared to systems that will slip. Okay. Kinematic design of gears mainly involve types of gears and gear ratio, which we'll talk about. So some different types of gears. So these are three main types. Of course, there will be many different kinds of designs. Spur gears, their teeth are cut along axial lines parallel to the shaft. That means, right, the shaft is here. Okay, this is the shaft. The teeth, they are parallel to the shaft. Okay, so you can imagine the shaft will be something like this, right? That's the shaft. You can see that the teeth, all these are teeth, they are in parallel with the shaft. Okay, and so the one that is attached to them, right, usually will look about the same design, because you don't want to match this with another kind of gear that will cause a lot of wear or slip. Okay, so spur gear, usually you will connect with another spur gear also. Okay, sometimes it can look like that also. So you have a track that will have a lot of teeth, and then a spur gear will be rotating, and then either this will roll on, it will seem like it's rolling on the track, or it will seem like this thing is rotating on a spot, and then the track being brought along somewhere, okay, in a certain direction. Another kind is helical gears. So teeth are cut along a helix, which is very similar to spur gears, just that the teeth, right, there is some angle to it. Okay, there's some angle to it. It's not straight cut anymore. Okay, this kind, again, you will connect to something similar also. Okay, do not have it slip so much. Bevel gears used with shafts inclined to one another. So bevel gears, they look like that. You see these are more special than the top two, right? The rotating one and the one that is caused by the first one, the rotation is caused by the first one, they are on different axes. Okay, they are on different axes. So if you have this kind of gears, right, you can change the direction of rotation. Okay, that's one use of it. Okay, so for gears, the most important thing to study, right, is this thing called the gear ratio. Remember, you can have a gear, and then the gear that is attached to the first gear, right, it could be bigger or it could be smaller. Okay, and that, how do we know whether it's bigger or smaller? We define using this thing called the gear ratio. So there are a few ways to calculate the gear ratios, because all these, right, they are proportionate. Omega is actually the angular velocity. Okay, angular velocity. The numerator should be the angular velocity of the driver gear. That means the first gear, the one that you are driving. The one below should be the driven gear. Okay, the one that is being driven. But if you look at it from diameter perspective, right? Diameter, that means the size of it. You see at the top, right, the numerator would be the driven gear. Okay, that means the second gear. Then below would be the driver gear. Okay, you think about it. So this diameter, right, it will be opposite from the angular velocity. Correct? The proportional of the magnitude. The bigger your gear go, the slower it should rotate. Right? The smaller your gear go, the faster it should rotate. Okay? And then this number of teeth on the gear, right? T, the proportion will be following the diameter of the gear also. This one more straightforward because a bigger gear, assuming you have the same teeth size and same spacing, the bigger gear should have more teeth. Okay, so down here, the diameter and the number of teeth should be more straightforward to understand. Then the sign is to indicate the direction. If both gears rotate same direction, the sign will be positive. But for a start, you all can just ignore the sign, okay? Gear ratio, usually we also don't usually say in negative numbers. We are just comparing the size and whether the speed is increased, whether the torque is increased. Okay, so that's gear ratio. Got other kinds of ratio also. These are more specific. One is the angular velocity ratio. That means literally we are comparing the angular velocity of the out, that means the driven one, to the driver gear. Okay. Then torque is the, I have to write out the formula first, okay, for you all to understand better. You all know for the same amount of power transmitted, right? The angular velocity and the torque, it will be going opposite from each other. Right? Remember what is the formula for power? Okay, we first learned that power equals to force times velocity, right? After that, when we study circular motion, we also learned that power equals to torque times omega. Okay, so if you see, to keep this P constant, right? If T increases, omega must decrease. Correct, and vice versa. Okay, this one is why these ratios are opposite from each other. One is angular velocity, the other one is describing torque. Basically, when you have two gears attached to each other, right? The size will determine the how fast the second gear will turn. All right, will determine how fast the second gear will turn. Then because the second gear, the speed change, right? But power must stay constant. You cannot lose power to nowhere, right? The power must be transmitted. So if the omega decrease, which is the angular velocity, right? If it goes down, torque must go up. You understand the concept? Okay, I say again. So for gears, you will have different size connecting with each other. Okay, so the diameter, right, the size will determine the speed, the angular velocity of the second gear. Okay, so when the angular velocity changes, that means this omega change, right? This torque must change accordingly, such that the power remains the same. Okay. Then there's another thing called a gear module. It's just a definition. Okay, so it's the diameter over the number of teeth. So basically, torque and velocity are exchanged for one another, like I had just described. When velocity reduces, the torque must increase. Okay, velocity reduces, torque increases. And when torque reduces, the velocity must increase. So they go opposite from each other. You all know, I think the best way to visualize this, right, is you all got drive manual car, or you all understand how car works, right? Or motorbikes are also same. So first gear, right, you will hear your RPM go up a lot. That means when you go into first gear, you will suddenly hear the engine, the speed, right, RPM increases a lot. You know why? What happened? When the RPM increases a lot, right, it is to match the second gear. Okay, we need to rotate the engine shaft very fast and connect it to something that is rather big. Okay, to match the wheel speed that you want to turn. Okay, so the very high speed you change to low speed. And visualize. So for gear one, right, you can imagine a simplified version, a smaller gear, which is the very high RPM one, then connected to a bigger gear. So this one rotating very fast, right? This one rotate slower. Your wheels, of course, rotate slower than the engine. Okay, in this way, right, the fast speed change to low speed, right? This thing, right, will allow torque to increase. The transmitted torque, you really boost the torque. That's why for gear one, right, if you need strength to climb slope, right, you will use gear one. Okay, there's a lot of torque transmitted to the wheels. There could be multiple gears, but I'm describing the simplest case. Imagine gear one, imagine the first gear is the engine shaft, second gear is already, you can imagine it as the wheel already. Okay, then as you travel faster and faster, if you stay in gear one, what happens? Your wheel speed increase, right? So your smaller gear speed also must increase to match. But why we cannot do that? Because the engine is not designed for the gear to rotate so fast. Engine cannot possibly exceed the amount, right? Let's say it can only run at max 6,000 RPM. In order for the wheel speed to increase, then the first gear, right, must go into 7,000, 8,000 already, but cannot. So for this thing, the second gear, the driven gear to rotate faster and faster, which is the wheel, what must you do? You must change the gear ratio. Okay, so that this thing can still rotate below 5,000, but the wheels can rotate faster and faster. Okay, you lower the gear ratio so that it is possible. If not, the engine cannot take it. But when you do that, right, as you lower and lower the gear ratio, that means you go gear 2, gear 3, the gear ratio will get decreased, right, to match the wheel speed. What happens? The torque decreases. Okay, so if you go up to gear 5 or gear 6, right, you will realize you go and try to accelerate, you can depress until the end, you won't get much power increase. Okay, because that is when the engine transmit the lowest torque. Okay, so that you can have the speed. You can't have the best of both, sadly. Okay, because power is limited. Okay, so this is how gears work. Okay, it transmits torque and angular velocity. It depends on what the angular velocity is, it will transmit a certain torque. Okay, let's look at one example. For the automotive gearbox shown, find suitable tooth numbers to give drive ratios of approximately 4:1, 2.5:1, and 1.5:1. All gears have a module of 3, and no gear is to have less than 15 teeth. So the first one, they want a gear ratio of 4. But before that, right, you have to find out certain stuff first. Okay, so the gearbox look like that. This is the input shaft. So this is the one that is trying to deliver power. Okay, then the input shaft you see is connected to the output shaft via some mechanism. Okay, this is one gear, right? It's connected to this lay shaft. Already there's a gear ratio here. Can you see? First one. Okay, this thing is turning. In turn, it will turn this thing. Okay, as a result, it will turn this thing, which will drive this shaft, and then all these other gears, right, will turn also. So it depends on which one you engage, which shaft you engage, which gear you engage here, right? It will determine the speed of the output shaft. Okay, so if you go and change to gear 1, gear 2, gear 3, it's actually changing which one is matching. Which one is matching. As all wheels have to have the same pitch and common center distance, each pair must have the same total number of teeth. This is to say, this whole thing, right, it needs to be centered here. Okay, down here also needs to be centered. So the sum of diameters for each pair, so this is one pair, like C and D is one pair, E and F is one pair. So each pair must have the same total number of teeth. So we can just analyze one pair and then it will be the same for the others also. Okay, so the sum of diameters equals to twice center distance. They tell you is down here they tell you is 72. So from the center of the shaft here, right, to the center of the other one is 72 mm. So if this 72, right, accounts for one part of the top gear and one part of the bottom gear, right, in total, the diameter of the two gears must be 72 times 2, correct? Okay, it's like adding the diameter up together. Okay, so that's 144. And then the sum of two numbers, that means how many teeth should it have, right? In the question, they tell the gears have a module of 3, and the definition of gear module is diameter over number of teeth. Okay, so this is 3, the diameter is known already. We can find the number of teeth. Okay, so the number of teeth is 48 for a pair. So for the first gear, right, they tell you you want a output gear ratio of 4. Okay, so from this gear A all the way until the end, down here they use G and H to illustrate the first gear. So A will transmit to B, then B, right, in turn will cause H to turn. H is connected to G and then will cause G to turn. Okay, so the total gear ratio, right, for this system is actually B over A to describe the first part. Remember, gear ratio is the number of teeth for the driven gear over number of teeth for the driver gear. So TB over TA describes this part. And then after that, right, the gear itself, the other side, when it's connected back to the output shaft, there will also be another gear ratio. Okay, so that one will be TG over TH. Basically, these two gear ratio put together, right, then is the total gear ratio. And they want the total gear ratio to be 4. Okay, they want it to be 4. And since sum of tooth numbers is 48 per pair, so TA plus TB must be 48. And then TG plus TH also must be 48 because this is one pair and then this is also another pair. And from here, right, this question needs some trial and error. Okay, so they say it is possible to make TB and TG equals to 32. That means number of teeth on B, right, and G to be 32. And number of teeth for A and H to be 16. Okay, so it's like trying to fit the criteria inside to see whether it makes sense or not. For this example, they tell you one of the criteria is no gear is to have less than 15 teeth. Of course, you cannot try less than 15. So in this case, they try 32 and then they also try 16. Okay, which will give G equals to 4 exactly. You want the gear ratio to be 4. Okay, then for second gear ratio, using the same system, so for second gear ratio, they want you to have 2.5. So second gear ratio, you see, also make up of two systems, right? One is A and B. Then this one, they use E and F to illustrate. So you must account for the gear ratio here for A and B, and also account for the gear ratio between E and F. So for gear ratio equals to 2.5, right? It must be TB over TA, account for this one first, multiply by TE over TF, account for the gear. Okay, and the whole thing must equals to 2.5. Down here, we put 2, right? It's for TB over TA, because we need to match our first part also. Because now we already settled with TB equals to 32, TA equals to 16. All right, we already know the number of gears for B and A already. So we have to stick to that. So if TB is 32, TA is 16, right? That will give you a 2. Okay, so down here, we only need to guess what is TE and TF. Okay, to match this condition. So what should TE and TF be for this to work out? It can be TE equals to 27, TF equals to 21. Could have other values also lah. Okay, but these are the two possible values, and they are both above 15. So it works out to be somewhere around 2.5. Okay, for the third gear ratio, you want the gear ratio to be 1.5. Same thing, first part you have A and B, that's why it's a 2 in front. Okay, then the next one you have to account for the gear. So TC over TD. And now you only need to guess your TC and TD to make it 1.5, near 1.5 lah. So this is how engineers design gearbox. Okay, this is how engineers design a gearbox. Okay, a very typical way to design gearbox lah. Of course, you need to know what kind of gear ratio you need first, right? You set that as what you want, then you go and design what kind of gears you need for this to work out. Okay, because you already know how much power you want to transmit for gear 1, how much power you want to transmit for gear 2. Okay, so this is an intro to mechanics of machines. Okay, all good? If all good, then we will go to 18. Okay, we'll start 18 before we take a break. Okay, is there a faster way to get the first assumption for gear ratio? Faster way to get the first assumption for gear ratio. I don't exactly know the question, but that is the usual way lah for engineers to design gearbox. Okay, but for studying wise, right, to guess here, guess there, maybe we are not so comfortable lah. So uh, quite unlikely to ask you to guess lah, in exam. Okay. So using the sum both 48, for example, T over TL, the sum is 48. Correct. You must match the criteria. That's why when you guess, right, when they guess, you see they use the number 27 and 21. Okay. And then both must be above 15 also. Correct. Oh, you mean for 32 and 16, how they get so fast, huh? That is if you have like okay, for real applications in a real gearbox, right? People will already roughly know the value already. Okay, so they guess almost quite soon already. Then they will continue designing from there. Of course, if you assume yourself to have zero knowledge, right, of what it should be, let's say for a real gearbox, you will have to keep trying. Imagine you do this, right? Then at the end you realize, cannot, this one cannot match. Then you have to restart again. Then you will end up with values that are quite close to that. Okay. But because that is already the solution, right? As in whatever I'm showing you the solution already. The guessing, right, takes time. It takes time, trial and error. Okay. 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 So let's start 18, which is planar kinematics of rigid bodies. So this is a slight revision. So for rigid body, right, it represents a system of particles. So at the start of the course, again, we always talk about particles only, right? Like 1 point. We always talk about wait, okay, we always talk about particle 1 point, but after that, subsequently we move on and then we study rigid bodies. Okay, so these rigid bodies, right, they are actually just a system of particles, objects that have many particles on it. Each particle on a rigid body has a different position vector because they are actually different particles at different space, right? So they will not have the same vectors. Okay, not just position, velocity, acceleration, all those may also be different. Rigid body has mass and rotational inertia. So only rigid body can have rotational inertia because only rigid body can rotate. Okay, single point cannot rotate. There are three types of rigid body planar motion. Again, also some revision because you already know this. First one is translation. Translation, that means you move it. Okay, you translate, you move it up, down, left, right. Okay, basically you just translate the item. It can be rectilinear or curvilinear. This is moving in straight line. These are moving in some sort of curve motion. Okay, but these are translations. So rigid body can also have rotation about some fixed point. That means when it rotates, the fixed point don't change. That's why we call it a fixed point. It rotates. That's rotation. The third one is actually a combination, and there is a term for it. It's called a general plane motion. Okay, basically moving along a plane generally. So that's why you can have a combination of translation and rotation. Remember, we study rolling motion, right? So that is actually one way, one type of general plane motion. So some illustrations. Rectilinear translation means you translate, you move things in straight lines. Okay, rectilinear. Then curvilinear translation means you also move things, move the items without rotation, but you will have some curves to it. May not be in a circle, okay, may not be in a circle. There's some curves to it. For example, if you have this plate swinging, right, because it's tied to here, you will see this whole plate swing left and right, okay, with some sort of circular motion. So as long as there is a curve, right, it's a curvilinear translation. Fixed axis rotation is something like that. Let's say you fix it at point A, and then you rotate it. Okay, the other point near the other end will move. Okay, that's a fixed axis rotation. If you rotate this, right, B will move to B prime. Okay, of course A will move because that's a fixed point. All other points, right, will start to move. So it's like a standard pendulum. Okay, fixed axis rotation. Last one is the combination, the general plane motion. Okay, so we have this object here. You move it, you translate it to somewhere on the right. All right. But now at the right, your A and the B, the alignment also changes. So there is some sort of rotation as well. You translate and then you rotate also. It's a combination. Example would be the connecting rod in the reciprocating engine. Connecting rod is this middle one. That's the connecting rod. This one is the connecting rod. So if you want to see the connecting rod, right, down here there's a GIF again. You see this connecting rod, it's not only moving from left to right, it is also rotating like this. Okay, if you can see my pen, this is rotating. Okay, rotation, but it's also moving at the same time. Okay, so it's a combination of both. So this particular structure here, right, as you see, it actually illustrates all three types. Okay, so it's the best way to see the difference of these three types. First one, the link OA, that means this one that's turning in circles, is a rotation about a fixed point. You can see this OA is a rotation about a fixed point. This B, right, this slider is only moving left and correct? It's only moving left and right down here. So that's a pure translation. And then, like I said already, the middle one that joins the two of them together, that one has a combination of both. So this crank and piston typical system that you see in engines, right? It actually illustrates all three. Okay, now we are coming to some equations parts, and then these are what you need to use to solve problems. Of course, put in some numbers. So consider 2 points, A and B on a rigid body. So let's say this is a rigid body. You have A here, you have B here. The motion of one point relative to the other point will be circular since these 2 points does not change. So if you have a point A and point B, these are the position vectors, right? From a fixed reference, which is somewhere else. This RAR is a position vector, and this is RB. This is RD relative to A. Okay, remember when we study our relative velocity, it's actually similar. Okay, so this is the equation that describes it. The second point here, right, is just trying to say on a fixed object, like this B, right, cannot translate away from A, correct or not? Because the object is rigid. It cannot move away from A. So if it changes with respect to A in space, it must be a rotation only. Okay, let's say if you are standing on point A, you don't care how this whole object moves. If you are standing at point A and you look at point B, right, point B will only rotate around you. Okay, point B cannot move away from you. If not, the object will break apart, correct? That's what point 2 is trying to say. Okay, the point relative to the other point will be circular. During the time, which is change in time, points A and B move to new positions. So for general plane motion, right, that means you translate and rotate. Both is a general motion. A will move to a new position in space. B will also move to another new position in space. Okay, so in time dt, this will be dra. That means the change in displacement for A. This is the change in displacement for B. Okay, we step by step lah. Okay, so this can happen. So the motion, right, that we just talked about in the previous slide is actually, it can be described using this 1 and 2. Okay, one is rectilinear translation. From here, right, imagine you translate the object to here. Okay, followed by a rotation about point A. So after you move here already, right, then you rotate the object a bit about point A such that it moves into another position. Okay, you see just now the object is like that, right, from here to here. Basically, it's from here and to the lighter part. Okay, you translate and then you rotate, it will be able to reach our final point that we see just now. Okay, so this equation will be valid. This is the standard relative kind of equation. For velocity, it will look very similar also, which we are going to see now. Why? Because velocity is just differentiating your displacement, correct? Your position. So if you go and differentiate them, right, everything to dt below, end up you are going to get something very similar. Okay, VB equals to VA plus BBA. Again, this B, if you write it like that, right, VB dash A means velocity of B with respect to A. Okay. So for kinematics, when we study kinematics and moving parts, all this relative motion, right, is actually quite important for you to visualize. Okay, we have touched on this at the front of the course, okay, 5-6 weeks ago, or maybe 7 weeks, because there was a break, right? Yeah. Okay, so it's the same equation. Okay, so this is our relative velocity. Or in vector form, if you want to write it in vector form, it will be similar, but this VBA, right, you can change it to this part, omega cross RBA. Because this VBA, right, that means the velocity of B relative to A. Remember we say it will only go in circles, right? You only go in circles. So we know it will be a circular motion, confirm one. And remember V equals to R omega, correct? In vector form, that will be V equals to omega cross R. Okay, this is actually a circular motion, describing that circular motion, okay, of B relative to A. Okay, that's why it's written in this way. Okay, so that's for displacement. We go into velocity of the points. Now we talk about instantaneous centers of zero velocity. Remember that time when we talk about rolling motion, right? Something that is rolling. I briefly mentioned this term and then I say later we'll touch on it. Okay, so this is a more general definition of instantaneous centers of zero velocity. So we consider a wheel rolling without slipping. Contact point represents the instantaneous center, IC for short. So if this thing is rolling, right, we can also see it as a rotation about this point. At that instant only, the next instant is not like that already. So at the instant, at any one instant that you see, right, the point of contact is actually the center of rotation. This whole thing is almost like it's rotating about this point. Okay, so this is the instantaneous center of zero velocity. As the term suggests, this point, right, will have no velocity. Okay, that's why we call it the instantaneous centers of zero velocity. That point, right, will not move. It will be zero velocity. And for rolling motion, it will be the point of contact without slipping, right? So the point of contact should have zero velocity. It's not moving at all. Okay, so now we talk about IC, which is the instantaneous center. Okay, velocity of a point is always perpendicular to the relative position vector from the IC to the point of interest. So remember, we come back to the rolling motion first because we studied this one before. So if the IC is here, right, and if you draw a line to the point of interest, let's say B, right, there will be a straight line, correct, connecting the two. The motion of B will be perpendicular to this line. Okay, from B to the instantaneous center, the motion, right, will be perpendicular to this line that's connecting them. That's why B, right, at that particular moment, B will be traveling in this manner. And same for C, a point like C, if you go and draw, right, C will be traveling towards this direction. Okay, it's not going down, it's not following the wheel, because at this moment, right, this whole thing is also moving to the right. Okay, so C will be like going in this direction. Okay, it's trying to move down, but then front also at the same time. Okay, so if you have an object like this, if you know the instantaneous center already, or sort of you have clues of where the instantaneous center is, if you join it to whichever point that you're trying to analyze, correct? The velocity of the point will be perpendicular to that line. If velocity VA of a point, A on a body, and the angular velocity is known, IC can be found from this formula. This is basically your circular motion. Okay, you can see this is actually your V equals to R omega, correct? This is the distance from A to the IC. Okay, the position of A relative to the IC, that means the distance between them. But for this particular illustration here, right, if omega is turning like that, of course, only this can be the IC. That's why you say in this illustration, only the one to the left and the bottom of A makes sense. Okay, this must be the instantaneous center. There may be situations where your guess is either here or here. But from the motion, right, you can confirm that the IC will be here. Okay, down here will not make sense, because when you turn, right, this will follow like this, and then this is the part that will be stationary. It will move. Next, if two non-parallel velocities are known, IC can be found by drawing perpendicular lines, and then the intersection will be the IC. So if two non-parallel velocities, in this illustration, right, you have one, this is the same object. You have point A going here, going upwards, and then another point, right, you know at that instant is going in this direction for B. If you go and draw perpendicular lines, one perpendicular to this motion, the other one perpendicular to the A's motion. And then this both imaginary line that you draw, right, the intersection will be the IC. Okay, so for this object, you see it's trying to rotate about this point. That's why B is moving here, A is moving up. Okay, so this is a characteristic of IC also. Then next, for parallel velocities, that means when both are moving in the same direction like this. If magnitudes and direction are known, IC can be found by using proportional triangles. So because it's parallel, right? And then IC is a point where it doesn't move. So a proportional triangle will bring you to a point where it will reach, where you intersect and then reach a point of 0. Okay, assuming this is the axis lah. Okay, if you have A that is moving fast in this direction, B that is moving not so fast, slower in this direction. If you draw a proportion triangle, right, there will be a point where it's like the particle there, right, will not be moving. All right, proportional triangle. So a point that will not be moving, that will be your IC, instantaneous center of zero velocity. Okay. And then point number 2, if VA equals to VB, IC will be located at infinity. So it's trying to say if you have 2 points here, imagine A and B, the length is the same one. You will not be able to draw a triangle, correct? You'll only be able to draw a triangle if one line is shorter than the other. Okay. So imagine for this example, the line is like that. Actually, you want to draw it properly. And A is down here. That's why you can draw a line, right? So imagine one is like that, then the other one also like that. How are you going to draw a triangle? Imagine they are perfectly straight. You will draw until the end, also cannot form triangle. So point 2, that's what it means. Okay. You will not have any IC. Okay, basically this thing that is describing if A and B is the same, right? It will be a translating body. Okay, it's not rotating. Then next, if magnitude and direction of two velocities are known by an opposite directions, for example like this, point A is moving to the right, and it's known, that's why the length you can draw it out as a vector. Then B is going in the opposite direction. Then the IC, right, can be found by joining ends to form triangles. So if you join the end of, imagine they are vectors and you draw it to scale. If you draw one end to join to the other end, right, wherever the intersection intersects at the middle, right, wherever it is, that will be the IC. Okay. So these few slides show the characteristic of this IC. IC means instantaneous centers of zero velocity. Okay, then some examples of IC. First one, if you imagine this is a wall and this is the ground. If you're going to put a stick like this, one part is resting on the ground, one part is resting on the wall. Imagine this is slippery, slippery enough. What will happen next? This thing will try to slide down, right? So A at that point will try to move left, directly pointing to the left because it's on the floor. Then B will try to slide down against the wall. So B will be sliding down. All right. So at that particular instant, right, the motion to describe the movement of this rod here, there will be some IC. All right, this structure is moving down, so you will be able to draw a perpendicular line, imaginary line. Okay, you draw a perpendicular one. Then this one is another point on the same object, right? You draw a perpendicular line. The point where these two imaginary line meets, right, that will be the instantaneous center of zero velocity. Okay, why we want to find this IC? Because this whole object at that particular instant, right, is like a rotation about this point here. Okay, then you can start analysis from there already. Okay, and this is another example of IC is if we have different points, right? And then the motion come together, the vectors converges to one point, right? That must be the IC. Okay, so some notes on IC. IC can only be used for a particular instant of time as body moves. After the instant, velocities may not be the same anymore. So it can only be applied at that particular instant. For example, like rolling motion. The next instant, right, after a small roll, your points change already, right? Change positions. So whatever you have analyzed for the previous time frame, right, it will not be applicable anymore. So it's only for the particular instant only. If you look at this structure also, it's starting like this, right? The moment where it slides, then this problem, you have the IC here. After that, the next moment, point B is not here anymore, right? It's not at this height anymore. It's somewhere below. So if you go and compute the next IC, it's totally different problem already. The IC also change position. Okay, so it's only applicable for a particular instant of time. IC is convenient for determining velocities, but not for acceleration, because IC generally does not have zero acceleration. So for this entire thing, right, these past few slides, we say instantaneous center of zero velocity. We never talk about acceleration, because only the velocity that we are trying to analyze is apparently not moving, correct? And then we can confirm that the velocity is zero. But how about for acceleration? You see, for any IC that we try to find, right? Let's say for this particular thing, IC is here. We know for sure the velocity is zero. But how about the acceleration? You don't know. Okay, it could, this IC itself could be accelerating somewhere. In this case, you see, the next instant of time, right? B will shift down, A will shift here. Can draw also lah. So next instant, imagine B is here and A is somewhere here. All right, if you draw imaginary line, the IC appears to be somewhere around here already, correct? So this IC appears to move from here to here, correct? So there will be some acceleration. Acceleration will bring it away. It's just for velocity, we can confirm that it's zero. Okay, so IC is not useful for acceleration because we don't know. Okay, so let's continue with this. Just now from position, we talk about velocity, right? How about for acceleration? Same thing. To find acceleration, you continue to differentiate. Just now we have VB equals to VA plus VBA, correct? To find acceleration, you differentiate. So the acceleration equation, right, will look the same also. AB equals to AA plus ABA. Okay, will look the same. But the usable form, it will look slightly different already. Okay, because for velocity, remember this component here, we know that it will be circular motion. But for acceleration, right, there will be more terms. Okay, since this is acceleration of circular motion, it can be expressed in terms of two components. Remember when we study circular motion, we have a tangential component and then another centripetal component, the radial component. Right? Tangential and radial. Basically, 1.2 is the middle of the circle, one is tangential to any point of the circle, right? So we have two terms there. This acceleration can be broken down into two terms. Normal and tangential. Tangential is the one we know. The radial, right? Sometimes we can also call it normal. It's actually the same thing, right? They're just different terms. So this is actually the normal on the radial one. This is the tangential part. Okay, can follow? Okay, hence, because of that, you can also rewrite the equation in this manner. Basically, AB equals to AA. Then the last term here, right, you break it down into two. It's illustrated here. Basically, this motion, it can be broken down into translation and rotation. So the translation is this part. Translation is the easy part. But for rotation, right, because we are talking about acceleration here, if you rotate, there will be a component pointing to the middle of the circle. In this case, it will be point A because we take relative to point A, right? B/A is B relative to point A. So we take A as the reference. So there will be a component pointing to A, and then there will be a component pointing tangential to the circle also. Okay, so concept-wise, this one makes sense and okay to understand, right? But for equations, it is not immediately usable. It's very difficult or almost impossible, right, to sub values into use like that when we do analysis. When we try to have problems and then we want to put values inside, very hard to put into this. So we need to have, we need to break it down further, okay, such that we can use it well. So for this equation, this is actually the same equation. We start from here. So acceleration of B must be equals to acceleration of A plus, this is the omega cross RBA, right? This is the velocity. Right, remember? Just now we talked about velocity. This is the velocity. Now we don't write it like that already. We straight away write it like this. Differentiate the velocity. Okay, then if you go and expand this out, at the start stay the same. These two terms stay the same. If you go and expand this thing out, it will be d omega over dt cross RBA first, plus omega times dRBA over dt. Sorry, cross. Okay, this is our cross product, and then you differentiate a cross product, right? It will turn out to be like this. Okay, then after this d omega over dt, right? We know you differentiate your angular velocity, you will get your alpha. That's why I change to alpha. And then at the end here, dRBA over dt, you differentiate your position, you will get velocity. This velocity, this whole thing. Okay, basically this whole thing, this is the velocity. Same as this one, this is also velocity. Okay, so it can be broken down in this longer form, okay, which can be used, and we will be seeing how we are going to use it the next example. Okay, so this is a gear example, double gear. The double gear shown rolls on a stationary lower rack. So the lower rack is not moving. The velocity of its center A is 1.2 meters per second directed to the right. Determine the angular velocity of the gear. That means the angular velocity of this gear. And the velocities of the upper rack R and point D on the gear. So you can imagine this is a gear that's attached to the one behind. Okay, and then this is stationary. At the bottom is stationary. This A, right, is moving to the right. This whole gear, when you turn, it will move to the right, correct? Because it's attached to some stationary rack. It will move to the right. And then this small gear here is attached to the upper rack. Okay, basically this setup, then they ask you this question. So angular velocity of the gear. Okay, let's look at what you are given first. Basically VA, that means velocity of point A, 1.2 meters per second. R1, 0.15. Down here, the dimensions given to you. So from here to the outer one is 0.15 meter. Okay, the outer radius, which is our R1. So to find the angular velocity, we just have to use our V equals to R omega. Okay, you use the velocity of A. This is actually a rolling motion. It's like a rolling motion. Below is like the ground not moving, right? This gear is rolling on it. So it's like a rolling motion. It's the same. So if the center is moving to the right, you just need to know the radius here. Okay, that's from the center to the sort of ground. You need to know the radius here. And then you just use V equals to R omega. You can find the angular velocity. Okay, so this gear is rotating with this speed, 8 radians per second. Okay, then for this question, we need to be clear on the vector directions because the equations that we are dealing with, they have cross product inside. All right, the direction will matter. So if A, right, the direction of the A, we give it, we write it as 1.2 I. That means we take the direction left and right, right? Right will be I, positive I. And then position of A relative to C, that means A relative to C, right? Imagine you are standing at C, where is A to you? A is upwards, correct? That's why it's 0.15 J. Okay, 0.15 J. Then this omega equals to minus 8K. You all remember how to get this? The right hand rule. All right. So you see here, back to the diagram. If I is to the right, down here, I is to the right, J is to the top. Where is K? Pointing towards you, right? Out of the screen towards you. That's the positive K axis. It's always the same one. Okay, it's pointing towards you. But you see this question is rotating to the right. So if you use your right hand rule, rotating to the right, your right hand should be the rotation motion, right? Your fingers. So if you're going to use your right hand rule, your thumb will be pointing into the screen. Okay, your thumb will be pointing into the screen. And so what direction should it be? K is pointing out, but you realize the direction is pointing into the screen. So it must be minus K, right? The direction of the rolling is actually minus K, minus 8K. So down here, right, when we study all this, the direction of all this becomes very important. Okay, direction becomes very important. You all can remember, right? There was this set of notes where we talk about the right hand rule. Okay, so your fingers follow where it's rotating. Then wherever your thumb point, right, that is the direction of the rotation. Yeah, so we have this value. Velocity relation between A and B, because they ask us to find velocity of upper rank R, which is this rank, right? That is actually the velocity of B. Okay, it's the same. Can you see? VR equals to VB because the rank is connected to this point B at that moment. So they must have the same velocity. So you just go and find VB can already. Okay, and from the equation, VB equals to VA plus omega cross RBA. This is the velocity equation. Okay, so you have VA already, 1.2 I. You also have omega minus 8K. The signs must follow must follow properly. Okay, in this topic. So omega, if it's minus 8K, right, you must really write minus 8K. Then RBA, that means the position of B relative to A is 0.1 J. Okay, you see the diagram again. Where is B relative to A? B is on top of A, right, by 0.1. That's why it's 0.1 J. Then from here, you go and solve this, will give you your answer, the velocity of B. Okay, you solve the one in the bracket first. Minus K cross something J. Again, is using a right-hand rule. Okay, remember? From this first direction, right, that you're talking about, then you curl your fingers towards the next axis. Wherever your thumb is pointing, right, will tell you the resultant. So in this case, you know where minus K is, right? It's inside, right? Inside. Then you want to cross J, which is pointing on top. So from inside, you curl out, and then wherever your thumb is pointing, right, the direction. So where is this pointing? I, all right, positive I. So down here, we'll give you a 0.8 I. So 1.2 I plus 0.8 I, you will get 2 I meters per second. So that will tell you the magnitude and the direction of this velocity, which is correct lah, because at this, you see, at this point, it must be going directly towards the right, right? For point B, it must be going directly to the right. So something that ends with I only is correct. Makes sense. Okay, then point D, actually the same. Let's use the same method. Okay, so velocity relation between A and D. So to find D is VA plus omega cross RDA. Exactly the same equation that we have used. So VA we know already, same one. Omega also same because it's the same gear, turning at the same angular velocity. The only difference here, right, between this one and the previous one is this RDA. Okay, you ask yourself, where is D relative to A? D is on the left side of A, right? That's why minus 0.15 I. That is the relative position of D with respect to A. Okay, some students confuse this one. Like if you, for example, if you put 0.15 instead of minus 0.15, wrong already, the whole thing. You can imagine after you work all this out, right, the directions will be wrong. Okay, you can ask yourself lah. So I mean, you can tell yourself D slash A, right? D with respect to A, right? Means imagine you put the reference at A. Imagine A is now the reference. That is the 0 point. Where is D? It is negative 0.15, right? Yeah, so it's negative 0.15. Okay, so down here, same thing. You go and work this thing out first. Okay, you'll be pointing somewhere in the J direction, right? K cross I, minus K cross minus I. Use your right hand rule, minus K cross minus I. You will end up pointing in the J direction, positive J. So you'll be like this. So you see, the motion of D, right, is actually a combination of something I plus something J, which is somewhere here. So at this particular instant, right, this part is actually moving to the top right. Because rolling wise is going up, but the gear is, the whole gear, right, is going to the right. Okay, that's why the resultant motion for D is pointing to the up and right, which makes sense. So if you get something like that for this kind of problem, you should think to be correct already lah. Okay. Okay, then we continue. Just now we use velocity only, right? We haven't even touched the complicated acceleration formula. So we continue from the same example. The center of the double gear in the previous example has a velocity of 1.2 meters per second to the right, which is same. But now they tell you it has an acceleration of 3 meters per second square to the right. So it's not just moving to the right. It's now actually moving faster and faster. Okay, there's an acceleration to it. Recalling that the lower rack is stationary, that means same situation, the lower rack doesn't move. Determine the angular acceleration of the gear. and the acceleration of points B, C, and D. Okay, so now we touch on acceleration already. So using the more complicated acceleration, because acceleration is more complicated. Okay, the longer equation. So this is what you have. Acceleration of point A, they tell you 3 is already given. So radius of that rolling motion is 0.15. So to find angular acceleration, that's easy because you'll be using A equals to R alpha. V equals to R omega, right? So A equals to R alpha, same thing. Not same thing, similar. Okay, so in this manner, you will be able to find the angular acceleration of the gear. Okay, so this part is solved already, the easiest part. So now we need to find the acceleration of those different points. So what's given? We have acceleration of A is 3 to the right, correct? That's why there's an I here. Now this part, right? Now this part is the part where all this ijk again is very important. Okay, then RA with respect to C, we also know is 0.15 J. This is position. Position. Then this angular acceleration, right? We calculated here already. The magnitude is 20, but direction-wise, same thing, right-hand rule. Okay, that's why it's a minus K. Okay, your thumb will be pointing into the screen for this case. Okay, now to find the acceleration of point B, okay, that's AB, we'll be using the long formula. Okay, this long formula is usable. We'll now see why it's usable. So it's acceleration of A. Okay, basically, I'm not going to read out. It's the exact equation that we have gone through, going plonk everything here. So acceleration of A, we know is 3I, it's moving to the right. Okay, omega, which is the angular velocity, we already know is minus 8K. So these values are known. Then RBA, which is B relative to A, what is the position, right? We know it is above A by 0.1. That's why 0.15 J. Then we continue. Plus alpha cross RBA, right? Alpha, we know is minus 20K. And then RBA, again, is 0.1 J. So you have the equation here already, right? Now you just need to carefully do all the cross products. Okay, of course, the ones in the brackets you do first. Then this one you do already, right? This minus 8K cross 0.1 J, you do already, right? K cross J will be pointing somewhere in the I direction. Okay, either I or minus I. Then after that, you will have to take something K cross something I. So do carefully. Okay, end up after you do, you will get this. Okay. So that's for point B, right? If you get the idea of how to find point B, find other points shouldn't be an issue already. Okay, basically it's applying the same equations but using different values. So you see, you want to find AC, correct? It's just the same thing, but now you, instead of B relative to A, right, you are using C relative to A because you are looking at different points. Okay, so instead of that, you will have to put in the correct values for C relative to A, the position vector, into this too. Okay, after you solve this carefully, you will get your answer. Then for point D, also same thing. Only this part is different. Now it's RDA. Down here is also RDA. Okay. Yeah, then we look at another one. Velocity and acceleration of a crank slider mechanism. So is this mechanism that we are looking at here again? Okay, so this is a schematic of that. If you have this OA turning, the angle at any time we'll call it theta. Then the other side, the connecting rod with the slider, right? There will be an angle to it, and you can expect this angle to be changing also. Okay, then this slider itself is moving left and right, correct? So if you take a reference from the right end, imagine this whole thing is straight. At that point, we'll take it as the reference for distance of this slider B. So slider B will move from 0 point and then increase in value, go back to 0, increase in value, go back to 0. Okay, that's why we draw like this from the right end. So you can imagine when this thing is functioning, right? All these stuffs, they are changing. X is changing, is theta changing. Okay, so to find the velocity, no, we are finding X first. Okay, to find an expression for X, that means at any point, right? At any point, what is this X supposed to be? In other words, where is the slider? You want to find where is the slider. Okay, you'll go through some mathematics. So basically, X is equals to R plus L. R is the length of this crank. Okay. Then L is the length of the connecting rod. Basically, you add R and L together, right? It describes the entire distance. All right, imagine they are a straight line. If you add R and L together, it's the whole thing. So what is this X? It's the whole thing minus this particular part, R cosine theta plus L cosine phi. R cosine theta is here, this part. This part, okay? R cosine theta is this part. Then L cosine phi is this part. Right? So you see, the first one, if you have to understand, right, is the whole thing minus these colored ones. That's going to give you the position X. Okay, so it's based on this. Then after that, you do some mathematics. R sine theta, which is this length here, this vertical length here, is equals to L sine phi, which is also this vertical length. Okay, so from here, you move L to the other side. Okay, sine phi, make sine phi the subject. I just briefly go through you all can go and read. So when I briefly go through, at least you all have an idea of what it's about. Okay, basically from here it's just mathematics. So you can square both sides so that you can continue working on it. In this solution, you square both sides. So everything must be squared. Everything must be squared. And then you go and add cosine square phi to both sides. Why you square after that? So troublesome, still going to add cosine square. Because you want to get this expression here. Sine square plus cosine square equals to 1. Okay? Sine square plus cosine square equals to 1. So right hand side, you leave it. Then you now make the cosine square the subject. Then you square root to find cosine phi. Okay, basically for this part that the solution is showing you is to find x, which is this distance, in terms of theta. Okay, theta is this angle. That means this crank, you know where it's rotating, right? At any point, you know the theta. Wherever this rod OA is, you will know the theta for that particular position. Okay, so it means with this equation here, right, you will know where B is if you know where OA is. Okay, basically this equation is to describe that. Okay. Then the velocity, just now we find a displacement, right, for the piston. Now we want to find the velocity of this piston, which is B. Whatever we have found just now, right, the entire expression for the x, you differentiate the whole thing. Okay, that's why you differentiate the entire chunk just now. Okay, so again, to briefly go through, you differentiate, right, R and L becomes 0. Okay, you do a differentiation, constants will become 0. Okay, then down here is theta. Theta is changing with respect to time, so that cannot be 0. Okay, so it's like differentiating this whole thing and also differentiating this whole thing inside also because there is a theta. Okay, so you differentiate this r cosine theta. When you differentiate cosine theta, you are going to get minus sine. Okay, then you must differentiate inside again. Okay, must differentiate inside again, change u. So you get another theta over dt. Then the right hand side, this part they haven't differentiated. Okay, they are just still rewriting the one inside in a form that you can differentiate. Okay, so down here, this one, this one, d theta over dt change to omega. Then inside here, this whole square root, right, is actually to the power of half. So what happens when you differentiate? The half you'll take down and then it will become minus half. That's why you end up with something like this. You see this slide, this is the next slide. You see this whole thing, it's very mathematics, right? So to really do like engineering designs all the way manually, you have to know your maths quite a bit also. Yeah, quite a bit also. But generally, personally, to study physics or engineering, I don't like to go so deep into maths because that will kill interest. And also, we will tend to focus on the wrong stuff. We want to understand the concepts. But all these, yeah, go and read out on your maths first, then come and look at this. If not, you all can Google also. You all can Google also. But basically the whole thing, right? The idea is to relate this motion to this motion. Okay, this thing is turning, right? The engine is turning. Then this slider is moving left and right. There will be some position, there will be velocity, there will also be acceleration. Is the next part. Okay, so now we want to find the acceleration of this slider B when this thing turning. How do we relate this to this? So we find V already, right? Same thing for acceleration. We go and differentiate. We go and differentiate the entire thing. Because now the velocity we differentiate. I got put some comments here lah, to help you understand better. So in this part when you differentiate, right, you'll realize this omega is treated as a constant because we are assuming this engine is rotating at a constant RPM. Okay? But of course, theta will still change. Theta will change. Okay? With respect to time. Okay, so now is the end of 18. So we just take a short break, 15 minutes, then we come and do the last topic. Okay, topic 19. So we'll start again at 8:30. Okay. Yeah, see you all later. Again, I will mark attendance based on this. So just stay inside here, but you all can go for a break. Same thing.
one. Nobody knows but you. Nobody but act on all depends on what show you all the way. Let me show you all the way. Oh, let me show you all the ways. Yeah, let me show you all the ways. Oh.
Okay, shall we continue? Okay, so let's continue. The last topic is on central force motion and space mechanics. So now there's this Newton's law of gravitation. Newton's got a lot of laws. So for gravitation, he also has this law. Every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of the masses of the particles and inversely proportional to the square of the distance between them. So this long sentence, right, it can be described using this equation here. Okay, so this is the gravitational force on each other. If you have two particles here, right, one is m1, one is m2, they're at a distance apart, that is your r. They will exert some attractive force on each other. Okay, and what is the magnitude of that force that they attract on each other? It's given by gmm over r squared. Okay, m1 is the mass of this, m2 is the mass of that, r is this one, the square, that means you times that 2 times. G is this thing called the gravitational constant. Okay, gravitational constant, and as the name suggests, is a constant value. So this capital G, right, is this value here, 6.67 times 10 to the power minus 11. Okay, that's the gravitational constant. So don't confuse our gravity and this gravitational constant. This is a constant, it won't change. But the gravity that we study, right, it can have different values at different locations. Remember, the gravitational force, gravitational acceleration, it can change. Okay, and but this G is for this equation, it won't change. Gravitation forces always act along the line joining two particles, forming an action-reaction pair. So if you have two particles, right, or rather two objects placed close to each other, okay, they will attract each other, and then that force, right, will be along a straight line joining the two of them. The force that you exert on Earth is the force that Earth exerts on you. So actually everything, there is some attraction one. Even between you and your laptop, you and the water bottle. Okay, the chairs between each other also will have, but this kind of attraction is very negligible if you go and work out the numbers, almost non-existent, because the mass very small. But the when we are talking about planets, right, Earth, Mars, Sun, all this, the mass is super big. So there will be this force that cannot be neglected. In fact, it's this force, right, that gives us the gravitational acceleration. Okay, we are the one particle, Earth is another particle, right? So we attract each other. Okay, but the Earth mass is so big that of course you will be the one moving towards the Earth. That's why we drop down, right? We drop towards the Earth. Okay, that one is the attraction force that we are talking about. So more general definition of weight, the weight of a body, a total gravitational force exerted on the body by all other bodies in the universe. We have been learning about weight, right? Weight equals to mg, but this is the more general definition. So when body is near surface of Earth, which is mostly the things that we are studying things near a surface of Earth, right? We can neglect all other gravitational forces. Okay, even planes are near surface of the Earth. When we say near the surface, it's like things that are living around us. Not near the surface are like another planet. Okay, we are talking about this kind of scale. So when we are near surface of Earth, the force that Earth pull us, right, will be the greatest. That's why we can neglect all other gravitational. Okay, so if Earth has mass me, then the weight of a body mass at a distance re from center, this is radius of the Earth, can be approximated to the radius of the Earth, because our distance from the surface of Earth is negligible, right? So if you put into the formula, it will look like this. Okay, GMM over R square, the same formula. So this is the mass of Earth. This is the mass of, let's say, us, is the small body. Then divide by RE square. This is the distance between us, the object, and the Earth, the center of the Earth. And since W equals to mg, you will be able to sub in here, W equals to mg, then this m will be eliminated. Okay, so you're left with G equals to Gm over R, like this. Okay, and radius of Earth is around 6380 kilometers. The mass of Earth is 5.98 times 10 to the power of 24. If these values are put inside here, right, that will give us G equals to 9.8. So this is the gravitational acceleration that we are experiencing at the surface of Earth. Okay, so people use this method to calculate the mass of Earth actually. This relationship, P equal to GME over RE squared. Because mass of Earth cannot be measured, correct? We cannot possibly go and weigh the Earth. So the only way to calculate the mass of Earth, how do we know that it's 5.98 times 10 to the power 24? Because G can be measured. You can do a lot of experiments. You keep dropping things from different places. You can measure what is this G. Then the radius of the Earth can also be measured. Okay, because you can technically lay a long ruler or you slowly measure, right? It can be measured. Okay, although could be tedious lah. But mass you can never measure because you cannot put it on a scale. So this is the only way to measure, to find out the mass of the Earth. Okay, one example to see how we can use the equation. An unmanned lander is sent to the surface of the planet Mars, which has radius, this amount, this value, and a mass of 6.42 times 10 to the power 23. The Earth weight of the Mars lander, that means the same object, when it's on Earth, is 3920 newtons. Calculate its weight and the acceleration due to the gravity of Mars at this distance above the surface of Mars. So they give you some info when you are at Earth, but now the same object you bring to Mars, right? What is the weight, the new weight and the acceleration Gm? That means the new gravitational acceleration. So the distance r from center of Mars is given by this plus this. Basically, this is our radius of Mars plus we want to know that is the distance above the Mars. So the distance that we are looking at is just basically adding these two up together. Okay, so this is the r that we are talking about. The mass, we are given information about the lander on the Earth, right? Data is 3920 newtons. To find the mass, which cannot be changed, we'll just use 3920 divided by the gravitational acceleration on Earth. That will give us the mass of this object. And the mass stays the same, cannot change. So at the mass, something that's 400 kg still is 400 kg. Okay, mass stays the same. So we have the mass ready, we also have the R. So what is the gravitational force, which is the weight? We'll be using this equation, GMM over R squared. G is this constant value, just sub in. Mass of Mars is given. Mass of Mars is given. It's usually the mass of the planet that makes this whole number significant. Can you see? This is times to the power 10 to the power of 23. A planet is so heavy that can give this some significant number. Okay, so anyway, this is mass of Mars, mass of the body, the lander, then divide by the R square. You'll get 194 newtons. This is the weight of the lander on Mars. Then acceleration due to gravity, you already have the force, right? To find the acceleration, you just divide by mass. Then you'll get a value. So this is the gravitational acceleration on Mars, which is 0.48. It's much lighter. not lighter. It's a much smaller value than Earth. Okay? Yeah. Now I move to another section, the gravitational potential energy. We already know what this is, right? But for this topic, we are going to look at it in a more general form. Remember, our gravitational potential energy is mgh, correct? We assume that gravitational force on a body is constant in both magnitude and direction. That's why when we go and look at energy, the time we say change in potential energy equals to mgh. That means we simply just take m times g times the change in height. But if we are looking at very large distances, because we are talking from one planet to the other planet, the height is not like 5 meters, it's very far away. When we are talking about distances like that, right, it moves away from the planet, or rather moves closer to some planet at a significant amount. So we cannot just assume change in potential energy equals to this. Because the further we move away, the weaker the force there is. The energy associated is very different. So we cannot simply make such assumptions anymore. So generally, is given by this formula. Potential energy is actually minus gmm over r. Okay, minus gmm over r. This is our potential energy. So the work done by gravity is the force times distance. Okay, force times distance from R1 to R2 over a certain distance, basically. Okay, FDR. So our F, right, is gmm over r squared, right? From our first equation that we learned in the previous few slides. F is gmm over r squared. So you sub that gmm over r squared into this equation, and then you try to solve it. Okay, in the end, you will get something like that. Gmm over r2 minus gmm over r1. This simply means that the work done by gravity, right, is the change in potential energy, which is correct. This is what we have already learned. Right, the change in potential energy must be the work done. Right, so this is correct. So for this new term that we're looking at here, right, this gravitational potential energy, this minus sign in front is actually very important. Okay, it's the minus sign in front that makes these equations make sense. Okay, if not, it won't make sense really. Because you think about it, you look at this equation, when body moves away from the Earth, R increases, correct? When we move away from Earth, let's say we move upwards, R increases. What happens when this R increases? This value will become smaller, right? But there's a minus sign in front. So it becomes less negative. Okay, can visualize, understand? R increases. That means you imagine you're on the surface of the Earth. Then you move away from Earth. Let's say you move 10 meters, you climb 10 meters, you move away. So R increases such that this whole term on the right, this magnitude-wise, it will decrease. But because there's a negative sign in front, it means this whole thing becomes less negative. Okay, and that is important because it means when you move up, your potential energy increases. This value becomes less negative. That means it increases. Okay, and since is this equation, the gravitational force does negative work. Remember, you move object up, gravitational force do negative work. Right, it does negative work. Then the opposite is true also. When you fall towards the Earth, when you fall down from somewhere, your height decrease, right? So your R decreases, this whole term on the right without a negative sign, when r becomes smaller, this whole term on the right becomes bigger, right? That means it becomes more negative. Okay, that means when you fall down, your potential energy decreases. It becomes more negative. Okay, so the minus sign is very important. Okay, so that's generally on gravitational potential energy. Now, the next section is on escape velocity, or sometimes the escape speed. It is the velocity required for a body to escape completely from a planet. You know, now we are on Earth, right? We are always being held. We always want to fall towards Earth. But if you move away from Earth, the force will get smaller and smaller. There will be a point where you can escape Earth. You will not get pulled in anymore. Okay, we want to find the velocity that is required for a body to escape, to break free. Okay, so we just straight away look at example, then we can find the equation to, to that escape velocity. 3 men were sent to a moon in a shell fired from Earth in Florida. Find the muzzle speed needed to shoot the shell straight up to a height above the Earth equals to the Earth radius. Part B, find the escape speed. That is, the muzzle speed that will allow the shell to escape from Earth completely. Neglect air resistance, Earth rotation, and gravitational pull of the moon. Earth radius, they tell you is this. Mass of Earth, they tell you is this. So now we are trying to solve it with the most simplicity. No air resistance, which is not possible because in real life, at that kind of speed, very fast speed, there will be a lot of resistance. And as this thing is going on, now the Earth is rotating. So dynamics are changing. And also, moon is quite nearby to us, which has significant mass. So that actually exerts some force on it also, but we neglect all this. Okay, we solve part A first. So we have something on the Earth's surface, right, which has already a radius from the Earth. Now they ask you, down here, you're at point 1, you're on the Earth surface, you already have a radius. Now they tell you, they want you to project this mass upwards, such that it can reach this point, which is 2 times the distance from the Earth's core. That means this distance here is 2 RE. Height above the Earth equal to the Earth radius. Okay, that means from here measure all the way to point 2 is 2 RE. And now you can use your energy conservation equation. At point 1, you have half mv squared. It is the point where you will shoot this thing up with some speed, right? Half mv squared. Then at point 1, you will put your general form of the potential energy inside here. Okay, which is minus GMM over R. That's for point 1. Then for point 2, the energy must be same, right? So for point 2, they just want you to have enough speed to just reach this point. And then at that point, right, you won't be moving anymore. So K2, kinetic energy at this point, 0. You're not moving. For potential energy at that point, basically the below the radius, right, you just use this new radius, which is 2RE. The equation is minus GMM over R, right? So the R becomes 2RE. Okay, down here. So rearranging this, we are actually trying to solve V1. We want to know the initial speed such that this situation will occur. So we are actually solving for V1. Okay, which can be simplified to this. G times mass of Earth divided by radius of Earth. Okay, you will get this. So at the surface of Earth, you must be moving already at 7,900 meters per second. Okay, then you can brake. Then you can reach this level. Part B is actually the same question, just that the distance here, right, is different. Just that the distance here is different. Okay? So at point 1, you want to project this thing such that you reach a point where you are no longer affected by the gravitational pull. So how would the equation look like? We want the shell belly to be able to reach point 2 at R2 equals to infinity with no kinetic energy left over. So again, if we apply the equation, right, kinetic energy at 2 going to be 0. Just nice. Be able to reach that point. So K2 equals to 0. Okay, then U2, which is the potential energy at this point, must be 0. So this is actually the key step. The potential energy goes to 0 at infinity. Okay, this is actually the key step. If you write the conservation of energy, right, to find the escape speed, the U2, which is the potential energy at that point, must be equals to 0. That means there's no energy left. So you sort of break free from the Earth at that point. So the equation will look something like that. Point 1, you will get half mv squared. This is U1, the gravitational potential energy at point 1. Okay, then on the right hand side is actually the energy for point 2 lah. But as we had described, K will be equal to 0. U will also be equal to 0. So you see, this is also one of the reasons why potential energy, right, is negative something. Okay, is negative something, then it will always become less negative, increases, right? Until where? Until it reaches 0. Okay, then it breaks free already. So you can imagine GMM over R, right? The equation of GMM over R. You can take a look at this, GMM over R. If this R keep increasing, you keep getting further and further away. This term, right, will keep getting smaller and smaller until the whole thing becomes 0. Here I'm explaining for the point 2. Okay, so following this, we same thing, we are going to solve for V1, which is the velocity at the start. Okay, if you put in the values, you'll get another value for this. Of course, this value, right, has to be higher than part A. Because part A, we only want to reach until Earth radius only, equals to Earth radius height. Now we want to break free from Earth. So of course, this velocity has to be much higher. Okay, so it's square root 2 gm over r. And so you see from this example, right, this is how we define the escape velocity using this equation. Square root 2 gm over r down here, okay? Square root 2 gm over r. So this is the velocity needed to escape from something like Earth. Okay, so this is the escape velocity. Okay, so now we come to the motion of satellites. So how satellite move? We keep launching a lot of artificial satellites around Earth, right? They'll go around Earth. So this is actually how it works now. So imagine launching a projectile from A towards B. A is here. Imagine you launch something like this is of course a simplified version. If you have a tower this tall, then it will be crazy. Of course, cannot be so tall, right? So if you launch something from here, you launch it straight, okay, like this, B. So whatever we have learned, what we have learned, we learned that if you have something close to Earth, it will be attracted. Okay, so the moment you launch, this object will get attracted towards Earth. So if you launch it too slow, right? You launch it along this straight line, it will fall immediately to Earth. If you launch it fast enough, first is the slowest, and second is a bit faster, 3, 4, 5, 6, 7, 8. Okay, so all these are increasing speed. Trajectories 1 through 7 show effect of increasing speed. 1 and 2, you hit the ground. So imagine you shoot something, right? You see at this point, 1 already hit the ground. You hit Earth. 2, you also hit Earth. It's only 3, 4, 5, right? When you launch it out, the Earth is pulling you back, right? But the Earth can't seem to pull you back. Okay, can't seem to pull you back. You won't hit the Earth, but it's always trying to pull you back. That's why you will enter this kind of motion. Okay, it's called a closed orbit. Because after that, it's going to return to the initial point, and then this will continue. Earth is still trying to pull you, so you will keep going in circles. Okay, you'll keep going in circles. 6 and 7, which is these two, you already launched too fast already. You already escaped from Earth's pull, gravitational pull. So you will not be in closed orbit. You will be in open orbits. Okay, so when people launch satellites, they have to calculate properly. They want the satellite to be in a certain orbit. It's calculated one, okay? Simplest case, circular orbits. Most artificial satellites travel in a circular motion. So they will travel like that, okay, around Earth. And because it's circular motion, right, the dynamics that you have learned for circular motion, it will also apply to all these centripetal force, centripetal acceleration. Only force acting is the Earth's gravitational force. So speed is constant. Okay, so you imagine a satellite moving. Why will it not slow down? Because there's nothing trying to stop it. There's no air resistance. There's outside is in space. Okay, there's only something, the only force that's there, right, is this force towards Earth. Earth is trying to pull it. That's why as it's moving forward, it's also trying to come back to Earth, but it will never be able to reach. That's why you end up in this perpetual motion. Okay, until something happens. Since circular motion, whatever we have learned, right? F equals to mv squared over r. Remember? F equals to mv squared over r. That's our circular motion. And in this topic, we also learned that F equals to gmm over r squared. Okay, so we substitute the whole left side with gmm over r squared. So if you make velocity the subject, you're gonna get an expression. So from this expression, it tells you that for a given radius r, that means at a distance from Earth, given radius, the velocity is fixed one. Okay, so you see, they will see how far they want the satellite to travel around Earth. Then they will have to adjust and set this velocity accordingly. And to find period, this is the equation. period is your distance divided by velocity, right? Same thing lah, this is circular motion. So 2 pi r is the circumference, which is the distance, then divided by the velocity. Velocity, we have gotten it from the previous slide. So basically, you just sub that in, you will get this expression here. And to find the total mechanical energy during orbit, that will be your kinetic plus your potential. It's moving, right? It's moving, that's why there will be half mv squared. And also it's at a distance away from Earth, distance r. So the potential energy, there will be some value also. So if you add this up together, this V, you can sub this equation in the previous slide into this V. Okay, that's how you get this. Then it will give you energy equals to this simpler expression over here. Let's look at this example. Suppose you want to place a 1000 kg weather satellite into a circular orbit 300 km above the Earth's surface. What speed, period, and radial acceleration must it have? How much work has to be done to place this in orbit? And how much additional work will have to be done to make this satellite escape the Earth? So 3 parts. First, they ask you what is the speed. So to calculate the speed, the equation is this one, right? Square root of gm over r. So we need to first calculate the r that we are looking at. This is the radius, right? First radius. Then we want the satellite to be 300 km above. So the r that we are talking about is this amount. With this, you can put into this equation already. Because g is fixed, mass of Earth also fixed. Okay, now we have the velocity. And to calculate period, you just take 2 pi r divided by the velocity which you have just found. So this is your period. In other words, it takes 90.6 minutes to go one round. Radial acceleration is your v squared over r because it's a circular motion. Okay? So it's the same formula, v squared over r. So down here also, there's a sentence here, if you are curious. Why is this value smaller than the 9.8 that we know? Because this whole satellite, right, is at a height 300 km above the Earth's surface, which is very far away. So the gravitational acceleration has already dropped to this. Okay? (300 km), just to let you get a sense of how high 300 km is. You know, when you take your normal plane, right, the cruising altitude is around 30,000 feet, correct? 30,000 feet is around 10 km. When you reach the highest already cruising, you almost cannot, clouds are very far below you already. That's only 10 km. Okay, this is 300 km above. It's very far away. Okay. Part B, how much work has to be done to place this satellite in orbit? We are talking about work, so energy. Okay, we're talking about energy. How to find the work that needs to be done? We will go and find out the energy at point 2 and then find out the energy at point 1. The difference in energy must be the work that's needed, right? So that's exactly what you should do. The energy at point 2 is given by this. Okay, remember there was this slide with this equation. Energy can be simplified to this. Okay, so we just apply it accordingly. Okay, with the mass of Earth, mass of the object, and the R that we are talking about. So the energy at point 2 is minus 299 times 10 to the power of 10. Okay, that's point 2 when it's already 300 km above. At the Earth surface, which is the point 1 that we are talking about, you also go and find the energy there. Okay, how to find? At point 1, it's not moving, right? You are trying to get it to move to there. So kinetic energy is 0, just resting there. Then the potential energy at the Earth's surface is minus gmm over r. This is the general potential energy formula. So if you put in the values, you will get this value. So energy at point 1, energy at point 2, the work done required, right, is just the difference. This is at a higher value, correct? Because there's a negative sign in front. So you take E2 minus E1, that's the amount of energy you need to supply to get it into that position. And part C, how much additional work would have to be done to make this satellite escape the Earth? So to escape, this is the criteria. To escape, total mechanical energy must be 0. Remember in the previous example when we find the escape velocity. Also, the criteria is to escape, there will be no energy left. Okay, so mechanical energy must be 0. And just now we have already found that at E2, right, which is in orbit, this is the energy involved. Okay, so now we want to move from here, minus 2.99 times 10 to the power of 10, right? We want to increase this value to 0. What amount of work will be needed? Will be this amount. So you need to supply 2.99 times 10 to the power of 10 energy to move it to a point where Earth will never be able to bring it back. Okay? Can I move to another section? These some new laws and observations that govern all these how planets move with respect to each other or with respect to the sun. Okay, so these are the Kepler's laws. It describes the motion of planets around sun. Why the planets move around sun, right? It's actually following all these laws that we are going to see. First law, each planet moves in an elliptical orbit with the sun at one focus point of the orbit. That means if you look at this diagram here, right? Let's say this S is the sun. You know planets move around sun, right? Okay, so this is the sun. If we have a planet moving around in some orbit, it must be moving in this manner. Either direction, it must be moving in this manner, such that if you have draw a vertical y-axis, right? There must be an imaginary S on the same from the same distance on the other side, and then this will form an ellipse. Okay, this is how a planet will move around a sun, not just in our solar system. Okay, you must follow these Kepler's laws. The sum of distances SP and S prime P is the same for every point on the curve. So if you have this ellipse here, the sun, the actual sun, and the imaginary point on the other side, right? If you draw two lines to wherever the planet is at any point of time, this sum must always be the same. Okay, must always be the same. Longest dimension is the major axis. So half length is the semi-major axis. So this is the major axis that we are talking about from the left to the right. This is the major axis, the red line. So this one, right? This A down here, A. This one is the semi-major axis. Then the minor axis is actually this one. Where I use another color. This is the minor axis. The shorter side is the minor. Longer side is the major. Okay, so you have semi, which is half of it. And the distance from S from center of ellipse is EA, where E is the eccentricity and has a number between 0 and 1. So from this point O, right, to where the sun is, we call it EA. That means A is this distance here. So we multiply by some number from 0 to 1. If it's 1, it will equals to A, right? If it's 0, this whole thing, it will just mean that the sun is right at the origin. That means the whole thing will become a circle. So we use this EA to describe how this ellipse will look. Okay, if E equals to 0, that means the sun is right at the center. It means the orbit is circular. Okay, actual orbits of planets are fairly circular. For example, Earth has E equals to 0.017. That's very small. So Earth rotating around Sun will have this E here as 0.017. It's almost equals to 0. Okay, so if you have an ellipse, if you go and draw an ellipse, it's like the sun is around here. Almost around here. Okay, the sun is almost around here because E is very small. Okay, such that the whole thing will almost look like a circle. Kepler's second law, a line from the sun to a given planet sweeps out equal areas at equal time interval. That means, imagine you have this orbit here, you have this orbit, the sun is here, you're orbiting around the sun like this. So sometimes you'll be further, sometimes you'll be closer to the sun, right? Okay, then as you go around the sun, right, there will be this area that you are sweeping. Per unit time, there will be this area that you are sweeping. Okay, then this law is trying to say the line from the sun to a given planet sweeps out equal areas at any equal time interval. Okay, so you see, right, can better illustrate because they highlight it. So if you are further, if you move from here to here at a certain amount of time, that means you sweep out this amount of area, correct? This is the area. But if you are closer to the sun, the law, right, says that in the same amount of time, you need to sweep out the same area. So if you are here, to sweep out this same amount of area, you need to travel faster, right? Such that you can have this area equals to this area. Okay, so sector velocity is the same throughout. And sector velocity is the rate at which area is swept out. Basically, it's the rate of change of area. Must be the same. So how do you get this expression? It's actually half times base times height, then divide by dt. So this sector, right, they approximate this to a triangle. Approximate this to a triangle. So this part down here, this small base, we call it RD theta. So half times base, which is RD liter, times height, which is the radius, you're going to get half R squared d theta. Then divide by dt, right? So you divide by dt. So it looks like that. So following this law, right, if you are closer to the sun, if your ellipse look like that, if you are closer to the sun, you'll be moving faster. Okay, to sweep out the same area. Third law, the periods of the planets are proportional to 3/2 powers of the major axis length of their orbits. Basically, it's just this equation. This A is the major axis, right? Semi-major axis. So just follow this equation. Okay. Then after that is supplementary question. So go and have a look on your own. Okay, so now I'm just going to briefly run through the formula sheet. Okay, briefly run through the formula sheet, but you all should know everything inside already. You all can see, right, the uploaded formula sheet. Okay, so this will be the formula sheet that you all will use. Wait. Okay. So at the start, this one is your kinematic equations. Remember the 4 kinematic equations. Okay. Then down here, 4, 5, 6, all this is different variations of it depending on your axis. Okay, but the easiest way to do this is just know your 4 equations. Then you know that the signs will change, right? Depending on your definition of the axis. Okay, I think a better way would be not to refer to 4, 5, 6. It's actually quite confusing. Okay. Then 7v equals to r omega. This one you already know, circular motion. V is just a differentiate r. V is your r omega. This is just rewriting. A equals to r alpha. Here's circular motion. Then an, n is like n and t, r radial and t. So n is like normal, right? That is the same thing as your radial acceleration or centripetal acceleration, which is given by v square over r. Okay, down here we see this thing rho. This is our radius of curvature. It's another way of writing the r that we are talking about. Remember, we also learned about radius of curvature, right? So it's actually v square over the radius of curvature. Okay, and then radius of curvature, if you need the formula, is here. Then 12, 13, 14 are your equations from when we're studying circular motion. Okay, you all can refer back to your notes. We're studying circular motion. 15, 16, 15 is energy. T is our T down here refers to kinetic energy. This U1 to 2, right, is referring to the work done. Okay, so we have some energy, U plus the work done must be the energy later. Okay, so kinetic energy equals to half mv square. Then T is kinetic energy. B down here refers to potential energy. The notation slightly different. The notation slightly different, but concepts all the same. So kinetic plus potential must be equals to kinetic plus potential of the final. Okay, and then potential can also be separated into gravitational and elastic. Okay, then 17 is come to your momentum already. mv plus, this is your impulse, equals to mv2. Okay, 18 is conservation of momentum. Basically, initial total momentum must be equals to final total momentum. 19 is angular momentum. So h is our angular momentum. This is our angular impulse. So same thing down here, total angular momentum at the start must be equals to total angular momentum at the end. And 20, this is your coefficient of restitution. (21 to 23), this is our kinematics in angular form. Okay, 24 is your V equals to R omega, but in vector form. We just touched on this just now also. Okay, then A equals to tangential acceleration plus normal acceleration. So like I said, normal acceleration is also radial acceleration, is also centripetal acceleration. They have different terms to mean the same thing. Okay, I equals to R square dm. This is our moment of inertia. I is our moment of inertia. Then moment of inertia equals to mk square. K is our radius of gyration. Okay. And 28 is basically your parallel axis theorem. Okay, this is our parallel axis theorem. You know something, some moment inertia already, right? You want to rotate it about an axis that's parallel. What you need to do, you need to plus md square. This is our parallel axis theorem. Then 29, now is for rigid body. The energy equation, of course, will be the same. T plus work done must be equals to the T later. But now because rigid body, right? What's the difference between rigid body and particle? The only difference is rigid body also can rotate. All right, so now the kinetic energy that we're talking about will have both components. We have the half mv square component. We also have the half I omega square component. This is rotational. Okay, this is translational. And down here is just the work done. That means the work supplied. Okay, it could be a force times distance, change in potential energy, your m theta, or this is for springs. Okay, then conservation of energy is the same. Kinetic plus potential must be equals to kinetic plus potential. Initial and final must be the same. Then here is our angular momentum. Okay, angular momentum. I omega plus your angular impulse must be equals to the angular momentum later also. 32 is the conservation of angular momentum. Actually, the concept is the same. Okay, 31 and 32. 33, 34, 35, 36 is just some shapes and the moment of inertia. Okay, so this formula sheet was done by another lecturer, lah, but the course coordinator said just use the same. Okay, so basically these are all that we have learned. Okay, then the next thing that I'm going to briefly go through is your assignment 2 lah. Just a recap. Okay, still got some time to do lah. 13 November. Still got some time to do. Wait, am I sharing the screen? Yes, I am. Okay, so just follow all these instructions. I won't go through this instruction lah because it's already written there. So basically, you choose one movie or game, or could be TV show, okay, that you want to talk about, then discuss any interesting engineering concepts that we have learned that can be observed in this movie or TV show or gameplay. Okay, so from topic 1 to 19, we have learned a lot of stuff, right? So in your assignment, you can just talk about certain scenes, then talk about the physics involved, which topic, and then assume some values to it, and then put into equations, calculate, and continue our discussion. So describe whether whatever you have calculated makes sense or not. Do you think these values will be applicable in real life? If not, then why is it like that? Or because the movie is making it for effects, for cinematic effects, because the game is for effects also, or games are simulations, right? It's for low spec phones, cannot run so high spec stuff. Yeah, things like that. But of course, the focus will be on the stuff that you all have learned so far, lah. Like your how you're gonna assume values and then put into the equations, whether you apply correctly or not. Okay. So generally is to test your understanding of whatever you have learned, and can you relate all this to something in real life or not? Something that's happening that you see, like a movie or a game you play. Okay, any questions? Actually, we have come to the end already of the lecture part. Then from here on is the tutorial part, which another lecturer will take you all, but that part, right, I don't know. I don't know the details. Okay, so any questions? For the tutorial part, if for the tutorial part, if the admin never give you all any instructions, means just follow the latest that they have told you, lah. Okay, because I may not know their arrangements. There is basically the course coordinator also, which is from RMIT, that's in Australia, right? Yeah, actually he's the main course coordinator. I'm not. Okay, I'm just helping him to take the lecture part of this course. Okay, so they may have certain arrangements for the tutorial, right, which I may not know. So if you all got any questions regarding the tutorial stuff, right, or when is it, whether it will be held, you can email the admin to ask, lah. Okay, you can email them to check. Any questions? You all got any questions? Should there be like minimum amount of topic concept, or just even one is enough for the assignment? There is no restrictions on that, lah. But usually because of the number of pages given, right? Usually we'll talk about a few, lah. Go in there a bit, talk about a few. If you talk about just one, right? Yeah, like writing a research paper kind of in-depth already. Because if you talk about one topic and you can hit 12 pages, that is very, very, very in-depth. So usually report will look like you screenshot something, of course, label the figure properly, label tables properly, reference it. If you get from certain website, right, you must put the reference. Okay, then you screenshot already, right? You put that as a figure, you describe whatever that you want to describe in that particular screenshot. Okay, then after you finish already, let's say you talk about concept for 1-2 pages, then you can move on to another scene already that you want to talk about, another new figure, then start describing again. Some other equation, some other values. Okay, so usually a few topic or concept. And then try to have a variety it's basically to show off your understanding. Okay, try to have a variety, talk about different concepts. Yeah, okay, yeah. Any other questions? Yeah, if not, just let me check the attendance one more time. Okay, well, I think attendance is fine. When would the first assignment result be out? I haven't marked yet, so I'm going to mark in the next few days. But I don't know whether it will be released to you all. I'm not sure. Okay, but I'll be marking in the next few days. So to answer your question, I don't know from your perspective whether it will be out lah. That one I'm not sure. Okay, you want? Yeah, no problem. Okay, any other questions? If not, then yeah, today we end about 1 hour earlier, right? Okay, that's all. And this will be the last time I see you already lah for this module. Okay, I could be taking you for other modules in future. That one I don't know. But yeah, last time I see you for this module already. So the exam questions not set by me, not set by me. I will know the questions and the answers, but they are not set by me. Okay, and yeah, so just want to thank all of you for attending the class lah. Okay, so far. Then if you all have LinkedIn, feel free to add me. Yeah, stay in touch. That's all. If you have anything else, just email me. Okay, and all the best to everyone.